Hello everyone. Today's homework is about to consider the steady flow of an incompressible viscous flows over a thin flat plate. So starting with the equations governing the flow, explain and discuss how and why certain terms in the equation can be safely neglected without in the boundary layer equations. Also we need to describe and explain the origins of the phenomenon of this separation. Okay, so first we know that in this case, incompressible viscous flow steady flows over a thin flat plate. The total equation of the motion for two-dimensional flows are here. So from equation 1 to equation 3. Okay, so whereas x and y are the horizontal and vertical coordinates respectively, and u and v are the horizontal and vertical fluid velocity, and p is the fluid pressure. So this is u and this is v, x and y. Okay, so a force is located in the planes y equals 0. So considering the non-dimensional reductions, the non-dimensional form of the governing equations are showing here. So this is the non-dimensional form of the governing equations. So where L is the horizontal length is scale. So L delta is the boundary layer thickness at x equals L, so which is unknown. So U, the big letter U, is the flow velocity, which is aligned in the x direction parallel to the solid boundaries. So the Reynolds numbers we can be expressed by this one, right? Okay. So next, if the viscosity is small without being neglectable, so the modifying effect appeared to be confined with narrow regions adjacent to the solid surface, so which is called boundary layer, right? Okay, so within such layers, the fluid velocity changes rapidly from 0 to its mainstream value, and this may imply a steep gradient of shearing stress. So inside the boundary layers, the viscous forces balance inertial and pressure gradient forces. So that is the inertial and viscous forces are of the same order. So we can express in this way, in same order. Okay, in some order. So this. And then, so the Reynolds numbers can be taken into the non-dimensional governing equations, and we have these two equations. So from 7 to 8, so we have these two. Okay, have these two. Okay, so when Reynolds numbers tends to infinity, or the kinematic viscous tends to be 0, so the pressure is consistent across the boundary layers. So in terms of the dimensional variables, the equations can be deduced. So the equations 7 and 8 so can be deduced. Oh, sorry. This is 7 and 8, and this can be deduced to this 3. Okay, so can be deduced to this 3 from the 9 to 11. Okay, so the upward flows become so strong at some point that the fluid flowed into the mainstream directions cannot fade. So some fluid in the boundary layers will then have to flow against the mainstream flows. So between the forward and reversed flow, there will be a separation lines ending on the wall. So in the region of the reverse flows, the velocities still have a vanish right at the boundaries, moving up from the boundary wall. The flows first moves backwards to the mainstreams, but further from the walls, it must again turn back to the join up with a mainstream. So the velocity gradient must accordingly be negative right at the boundary in the reverse region, and the wall stress vanished. So which indicate that the boundary layer separation may happen. So from these figures, so we can see that the separation point. Okay. Okay, thank you.